Our recording. So in today's experiment, we're looking at lab 8A and 8B, which are esterification reactions, more specifically the Fischer esterification reaction. In lab 8A, we're preparing ethyl laurate, which is prepared from dodecanoic acid, also known as lauric acid, and ethanol. This reaction is catalyzed by hydrochloric acid, which is generated from acetyl chloride. Because this reaction is run with excess alcohol under catalytic acidic conditions, this is known as a textbook Fischer esterification reaction, which we've seen previously in lecture. So treatment of lauric acid or dodecanoic acid with ethanol in excess and catalytic hydrochloric acid upon heating gives us the esterification product ethyl laurate. In terms of the mechanism for this reaction, first let's talk about how the hydrochloric acid is generated. So the hydrochloric acid in this case is generated from acetyl chloride. This is a useful method to prepare anhydrous or water-free hydrochloric acid. So in this case, acetyl chloride reacts with ethanol. We have collapse of our tetrahedral intermediate, and then this resulting ester is then deprotonated by chloride to generate a trace amount of hydrochloric acid along with the following ester product. This ester byproduct is generated in trace amounts and can be easily removed via evaporation. Any questions on the first part for this mechanism? So we're able to generate catalytic amounts of hydrochloric acid from acetyl chloride and ethanol. Once we've generated our hydrochloric acid, we're now looking at a textbook Fischer esterification mechanism where our carboxylic acid is protonated, the activated carbonyl carbon is attacked by ethanol, the tetrahedral intermediate is then prepared to kick out water via deprotonation and a proton transfer to activate this hydroxyl group as a leaving group. Finally, we kick out water, and as a cleanup step, we deprotonate our ester to give us our final Fischer esterification product. In this case, the equilibrium favors the product because we're using an excess of ethanol. Does this Fischer esterification mechanism make sense to everyone? Any questions? Sure, one moment. There's the full mechanism, both for the generation of hydrochloric acid and the resulting Fischer esterification. Did that answer your question? Okay, so once we've generated our ethyl laurate product, let's talk a little bit about how the product will be isolated and purified. First, we're concentrating our reaction mixture and then extracting and rinsing our reaction mixture with water and sodium hydrogen carbonate. This is designed to remove any traces of ethanol or hydrochloric acid remaining in our product mixture. After rinsing our organic layer and extracting our organic layer with water, bicarbonate, and then water once again, our organic layer will be primarily enriched in the ethyl laurate product. To further purify this ethyl laurate product, we're going to purify it via a silica gel plug. where we elute our compound through a layer of silica gel using dichloromethane. This would give us a solution of ethyl laurate in dichloromethane, which will then concentrate via evaporation to give us our pure ethyl laurate product. To characterize our product, we're going to run the hydroxamate test, which we've seen the mechanism for in previous labs. And a positive hydroxamate test for esters occurs when you make this hydroxamate derivative, and upon treatment with iron trichloride, this iron complex has a characteristic red-violet color. A positive hydroxamate test indicates that we have an ester. Carboxylic acids generally do not give positive hydroxamate test results. We're also going to be looking at the infrared spectra, which will provide evidence, because if you look at the carbonyl carbon as well as the carboxylic acid OH stretch, those are quite definitive clues for whether or not you've generated the ester product. We're also going to take a proton NMR, and you can look for these ester protons, which are highly indicative for the ethyl laurate product. Finally, we're going to take a boiling point and refractive index of our product, and then we'll calculate the mass and percent yield based on the isolated mass. So that's it for experiment 8A. Does everyone understand what's happening for experiment 8A? Okay. So let's take a look at 8B, which is the synthesis of isoamyl acetate, also known as isopentyl acetate, which is a principal fragrance often responsible for a banana smell in many common fragrances and foodstuff commodities. So isoamyl acetate is prepared also through a Fischer esterification, this time between isopentanol and acetic acid using catalytic sulfuric acid and heat. After we prepare isoamyl acetate, we're going to isolate and purify isoamyl acetate, first via concentration, then rinsing the mixture with water, bicarbonate, and water. And finally, once we have our organic layer, what we're going to do is we're going to distill the isoamyl acetate product via simple distillation. From here, we'll characterize the isolated purified isoamyl acetate via infrared spectroscopy and proton NMR. We'll take a boiling point and refractive index. And finally, we'll use the isolated mass to calculate the percent yield. As a final test, we'll also look at the solubility of both of our ester products in water, sulfuric acid, phosphoric acid, and hydrochloric acid. It's to note the esters generally are not soluble in water, but are soluble in concentrated acid solutions. So that's all we really have for experiment 8A and 8B. They're relatively straightforward experiments. You're going to write a single report for both experiments, and the lab page containing the recording is already up for 8A, and 8B will be up for next lab period. You'll write a single report for both of these lab parts.